Hi everyone, my name is Daniela and I am super excited to be here. I'm also very honored that I was invited to be part of the first edition of iOS conference here in Skopje, which is my hometown. I would also like to ask you, before I start, for a big round of applause for Christian. Big applause, everyone. I don't see him in the audience, but I really enjoyed his talk, and having the icebreaker presentation is never easy, and you did a fantastic job. Also, after the talk about spatial computing and Visual Pro, talking about clients and servers feels very mundane, but I will do my best to keep your attention and to teach you something, hopefully, about gRPC and protocol buffers. Even though we might think that clients and servers is a mundane discussion, it is very important to utilize technologies that abstract those concerns from our applications so that we can focus on the important parts, like accessibility, fancy UI, and other capabilities. And in a client and server architecture, very often the discussions are very server-centric. And a lot of the technological decisions and setups are usually made and discussed from a server standpoint. I disagree with that approach because I think that the decisions that are made when we set up the client and server architecture have profound effects on our clients. These technologies and this setup can have big impact on our applications' efficiency, scalability, security. But this setup also can impact how we write a big portion of the client code. And finally, it can also have impact on the client's capability. Most typical capability that we would expect to be supported in a client-server application is the capability for the client to send HTTP requests to the server and for the server to respond with some form of HTTP response. The ones from the audience that will say, but wait, an HTTP is just an implementation detail. I will agree. Yes, HTTP is just an implementation detail that sometimes gets exposed to our clients, but essentially we would only want a client that makes requests and receives some sort of response from the server. And that is the basic capability that we would expect in a client-server scenario. This type of communication is called a unary communication, and this use case is solved by many frameworks and libraries in efficient and elegant ways. In this problem space, we have many RESTful frameworks that are very popular. We also have GraphQL, but we also have gRPC as an option. However, sometimes clients need more capabilities. Servers need more capabilities as well. Sometimes just simple request and response is not enough to get all the data that we need. Sometimes data is not readily available for us, and the server needs to stream the response back to the clients. Unless we want to implement some sort of polling, server polling, by using the unary calls, we then need to keep an open connection to the server so that the server can stream their responses to our clients. The problem space here, again, has many solutions. For instance, what was the name? Sorry, GraphQL subscriptions. My mind went blank for a minute. GraphQL subscriptions offer solutions to this problem, and there's also gRPC. We could also be using some lower level frameworks like WebSockets. or lower level solutions. Sometimes we need to flip this use case, and we need to enable our clients to stream data to the servers in a similar way. So we still need to keep some sort of connection open between the clients and the servers. However, the problem space here, the solution space here, is even smaller. gRPC is probably the only high-level framework that could be used to address this use case. But we could be using some lower-level frameworks like WebSockets or maybe even WebRTC. And finally, what about two-way streaming? Sometimes we need the client and the server to keep a two-way connection so that they can stream data to each other. And unless we want to use WebSockets or WebRTC or some other similar technology, gRPC is probably the only solution that we would want to use in this case. So I would like to say that there's no one-size-fits-all unless you're using gRPC. gRPC is a framework. It's a full-blown framework, not an architectural style. It is a great framework. It is built open source by Google, mostly Google, and it's been open source since 2015. But it was used internally by Google for nearly a decade before that. So in that sense, it's a very mature technology. Google used Stubby, which was the gRPC predecessor, to achieve microservice architecture at scale. The desire was to be able to create many narrow-focused, single-purpose microservices that will easily call each other in a remote procedure call manner. To achieve this at scale, the only solution was to abstract a lot of the network communication and complexity. And to do that, Google created Stubby, which later became gRPC. Before I continue, I would like to introduce you to the golden retriever Pancake. Pancake is the gRPC ambassador. And it's a well-beloved community figure, and Pancake often makes appearances in many demos and talks about gRPC. And this talk will not be the exception. Let's take a deep dive into the basics of gRPC. gRPC has an IDL-first approach, and the choice for IDL stands for Interface Definition Language, and the default choice for IDL in gRPC are protocol buffers. Because protocol buffers are used, gRPC offers efficient and compact binary serialization of our messages. gRPC comes with runtime and developer environments, and with support for many of the most popular languages. These developer runtimes and environments enable developers to quickly get started with gRPC, but also to quickly scale their solutions at scale. Finally, gRPC has HTTP2 support, which comes with a lot of benefits. So the two-way streaming is one of them, but there's also built-in authentication and also channel multiplexing. However, HTTP2 is also an implementation detail, and gRPC offers support for other protocols that have similar capabilities, for instance, the QUIC protocol, which is implemented by Cronet. Let's take a look at the developer runtime and environment that I mentioned. Each application that is written in a certain language will interface with the gRPC library through gRPC-specific stubs that are created for that particular language. The stubs will also enable the application to use interceptors to further customize the services. The stubs then will interact with gRPC library. For instance, if we are using Python, this will be a Python gRPC library. And this library is usually a thin wrapper on top of the gRPC core library, which is written in C and C++. This core library is the part that implements most of the networking, authentication, scalability, and other important aspects of gRPC. The language stacks, of course, differs between different languages, depending on API and other capabilities the languages offer. For instance, the Swift language stack looks a bit different than most common gRPC language stacks. The biggest difference is that the gRPC Swift library recently was rewritten to replace the gRPC core library with Swift Neo, which is Apple's super performant networking library. And we'll go into detail about that in a bit. So gRPC, it is very difficult to talk about gRPC without talking about protocol buffers. Protocol buffers offer serialization mechanisms for structured data and services, which are very efficient on the wire, both in speed and in compactness. And even though gRPC and protocol buffers are often mentioned together, and they are often considered to go hand in hand, I would like to stress that protocol buffers are a perfectly viable solution to be used on their own. For instance, if you need an efficient data storage, or if you need efficient network transport. Also, for all situations where you need strongly typed schema enforcement. For instance, at Google, for one of the products that I worked at, or worked for, we used protocol buffers to define analytic events so that we could share the same analytic events between all the platform and the data team. So, like I said, protocol buffers offer serialization mechanism, but they also enable definition of data structures and services. To be most efficient, this data representation is expected to be several megabytes in size. And of course, you could be using protocol buffers to serialize bigger pieces of information, but then performance will take a hit. To use the protocol buffers to serialize, deserialize message, and to access their fields, you will need to use Protocompiler, which is also open source and available for many languages. Finally, protocol buffer messages inherently don't describe their schema. And furthermore, it is very difficult to interpret protocol buffer messages without the schema at hand. That means that the schema is strongly enforced, and we cannot use the messages without the schema. This might mean that backwards compatibility is difficult, but it's the contrary. Protocol buffers very easily allows for backward and also forward compatibility, meaning that old clients can easily serialize and deserialize new messages, but also old clients can, and new clients can also take advantage of old types of messages. And this is done by following simple best practices. I know that was a lot of theory, but now let's look at some of the practicalities of protocol buffers. Let's say we want to create a schema describing the attendees of this conference. So for each attendee, we would want to store the name, mail, phone number, maybe even food preferences or allergies. We could even use an enumeration to keep track of the types of attendees we might have on the conference. And finally, we could store all of those attendees in an address book. I would like to point that here, the first line is defining the syntax of this proto. And if we omit this definition, then the default proto syntax to be used will be protocol buffers 2. You might have noticed that the fields of the message had a certain structure to them. So a typical field message will have a field label, field type, field name, of course, and also a field number. And this is the thing that usually causes people to scratch their heads the most and is the most confusing. The label can be optional, repeated, or map. And if omitted, then the default label, which is called implicit field presence, is applied. Protocol buffers offer a wide support for all scalar types that you would expect. There is also support for enumerations. And finally, you could be using other message types as field types for your protocol buffer. And the number. The number is any number in the range from 1 to 500 million, which is 2 to the power of 29 minus 1. This number must be unique in a message, and numbers cannot be changed once the message is in use. Also, reusability of numbers within a message is very strongly discouraged because it leads to a whole class of bugs that are very difficult to track. Another thing to remember about this number is that lower value numbers, for instance from 1 to 15, are encouraged to be used for fields that are that are frequently set and accessed. This is because numbers from 1 to 15 will use only 1 byte on the wire. If you're following this simple best practice, you will also be following the practice to not bloat your messages and to keep short and concise messages in your protocol definitions. Once we have the protocol definition, the protocol schema, the protocol definition in place, we put it in a proto file, which then needs to be run through the compiler. The proto compiler, the default compiler, has support for some languages, and for other languages, it needs a special plugin. Once the proto file is run through the compiler, then specific source files will be created, where the data structures will map to class or structs, and the service definitions will map to client or server stubs. For Swift, there is a Swift Protobuf plugin, which is created and maintained by Apple, is also open source. And this compiler only maps the data structures into structs. The client and server stubs, we will talk about how we get them in a little bit. This protocol buffer plugin creates, you will recognize the output from this plugin because it will have the extension .pb. It creates a Swift class with containing the struct that maps the data structure into a Swift structure. For purposes of this talk, I've created a simple demo application. The demo application will be a chat room where the attendees of this conference can send and receive messages. So to get started, I first created a protocol definition, a proto definition of the chat message data structure. And it doesn't have to be anything fancy. The chat message can only contain information about the attendee that sent it and the textual value of the message. After creating the data structure and writing it in a proto file, then that file needs to be compiled so that we can have the source files. A note on the Swift plugin, Swift Proto C plugin. At the moment of writing this presentation, there are two ways to obtain that plugin so you can have it locally on your machine to create the output files. You can either build it yourself, or you can use Homebrew. I recommend using Homebrew. Another piece, another missing functionality to be able to access the generated files is the Swift Protobuf runtime library, which you will need to add to your project through Swift Package Manager or Cocoa Pods. And once we compile the proto file and we run it through the compiler, we then get a Swift file that contains the Swift structure. It might look a little bit chatty with all the comments and a lot of other fields, but it essentially allows accessors for the properties as well as serialization and deserialization functions. However, it is very seldom that you will need to use those serialization and deserialization methods yourselves with gRPC. Another important thing that I want to mention here is that proto optionals, you remember there was a label through which one could set a field to optional, and Swift optionals are not the same thing. Sadly, proto optionals define only the presence of the field or the abstinence of that field on the wire, meaning will this field need to be present in the well-formatted message or not. However, when deserialized, the default implementation will always, generated implementation will always have a default value. This is a bit weird, and it requires a little bit of a weird dance where you have to clear the message, clear the property, and check if the property was set, when Swift has a perfectly viable optional support. However, I've seen some of the discussions around this on GitHub, and this support might be coming down the line. But it is very important to note that currently Swift optionals in their true essence are not possible with protocol buffers. How does this tie in with gRPC? Like I said, I created a demo app that is a chat application. We have the data structure, but what do we do with it? We create a service. And a chat application has a chat room service, which has one procedure to it for now, which is to add a message. This procedure, let's call it a procedure, but for all intents and purposes, it's a function. Accepts a chat message as an input and will return a chat message, just for simplicity. If you remember this flow, let's refer to it to the Protobufs flow. So we took our proto file and we ran it through the Swift plugin compiler, and we got our Swift structures. I told you that we'll get to the bit where we talk about client and server stubs. So there's an additional plugin, and yes, I feel your pain. I also feel that it's a bit excessive to have two plugins. But with this additional plugin, we can create our client or server stubs. And you will recognize them because they have the .grpc suffix. So if having two compiler plugins is not enough, this plugin also is installed a little bit differently. So currently, there's no Homebrew support to install the gRPC protocol buffers plugin. So this plugin, you will need to build it yourself. However, not everything is super terrible. There's also a Swift Package Manager plugin that you could use in Xcode so that you can generate your output files during build time as opposed to building them ahead of time and adding them to your projects. And once we run our newly created proto file with all the data structures and services in place, when we run it through the compiler with the gRPC plugin, then we get source files with client and or server stubs. The generation of client or server stubs is just options that can be passed to the compiler. So the client stubs will be generated for us, or the server stubs. And let's see, how do we use them? To call the API through the client stubs, we first need to create a client. And the client is provided by the gRPC Swift library. This is a library that is available through Swift Package Manager or Cocoa Pods. The client that I've used in the demo app is an async client and is based on Swift concurrency, the latest Swift concurrency. However, if you can't use Swift concurrency or in your app, or you don't want to use them, there's client API that relies on concurrency provided by Swift Neo. There is a little bit of more of implementation details exposed here, so you will need to know a little bit more about Swift Neo to be using those clients, but the functionality is the same. These 3 lines is all that it takes to define a client that is capable of sending a request to a gRPC service. So there's basically not a single line of code that's been omitted. And I want to stress that. The demo app is a simple demo app that adds a message for now. And the textual message is wrapped in a chat message, which is the structure corresponding to that was generated with the protocol buffer compiler. And to send this message to our server, this is all it takes. This is the line that will send the request to our server, that will serialize our Swift structure into a Protobuf message, that will make all the networking requests, that will, if we use authentication, that will do all of the network authentication for us. And then it will wait for the response. The response will be serialized and will be readily available for us. And I think that that's pretty powerful. Like I said, I've also created a server application for this demo, and the server implementation is equally easy to accomplish. The only additional complex things is that I added a print statement. But if we say that our server just reflects back the incoming message, then we just need to return the incoming request in our server implementation. And this is how it looks in action. The console output that you look at is the console output from the server application. So it will receive the incoming message and will reflect it back. And then the client will use that application and use that message and display it in a text view. Okay, we have a chat room. We can add messages, but to really make it a functional chat client, we need to also receive messages that other attendees have sent. So this is, if you've been following this presentation, this might be straightforward for you. Because we know that gRPC supports server streaming. So we can add, one additional procedure definition where we can get all the messages and they will be streamed to us. However, I don't really like the fact that we need to make additional requests for all the messages that the user might input. And if you've been paying attention to the presentation so far, you know that gRPC offers bidirectional streaming. So that means that my service for the chat room can have just one procedure. The clients can simply connect to the chat room. They can stream their messages through an open connection to the server, and then the server can stream the incoming messages back to the client through another stream. So this is all it takes to define a fully functional chat room service. And this is pretty easy. But this is a proto file, right? Maybe the implementation is a little bit more complicated. Maybe, let's take a look. If we run the newly created proto definition through the compiler, this is the stub that we will get. The stub will provide us with a bidirectional stream provided by the gRPC library. So all it takes for us in our client application is to make sure that every time the chat room is loaded or appears, depending on our preferences, we modify our call from this to this. We make the call we connect to the chat room. And we are provided with a bidirectional stream object through which we can access the response stream. The response stream is a simple async sequence. So we can just wait for incoming responses on that sequence. And every time we get a response, we can simply update our UI. To send the messages, we need to modify the point in our code where we were making one request at a time to simply send asynchronous requests to the stream that was provided to us by the library. And that was all it took to upgrade from one unary call to a bidirectional streaming. It was really that easy, and I omitted very little code. You will see the demo projects will be available so you can see for yourself. The things where it might get tricky is the server implementation, and this is an iOS conference, but I will still walk you through how easy it is to implement this even server side. So the tricky part here is the fact that we need to store a reference to all the request streams so that we can broadcast our messages to all the people that have connected to the chat room. And since the server provider is sendable, we need to make sure that this happens in a thread-safe manner. And we can do that by using, by wrapping that storage in an actor class. I know that there is a talk on Sendable tomorrow, I think, so I'm very excited to attend that talk and learn more about this topic. But once we have our actor that will have safe storage, that will safely store all of our requests, streams, then every time that we receive an incoming chat message, we will just broadcast that message to all streams. And this is how it looks in practice. To simulate a multi-client environment, I've simply started two simulators. This is the most common way of testing this type of things. So the one client will send a message that will be received by the server and broadcasted to all other participants. Same goes when someone else sends a message, which will similarly be broadcasted to everyone else. And that's all it took to create a very simple, but still fully functional, not just client, but also server chat room. And I think that that's very powerful. I think that that showcases how quickly and easily you can get started with gRPC and protocol buffers and create really, really powerful solutions. With that being said, I think there are some important considerations that need to be addressed when talking about gRPC and protocol buffers. yes, there are very powerful technologies, and you can do very powerful things with few lines of code. However, they are not a silver bullet, and if you want to consider them for your current or upcoming projects, I think you should ask yourselves several questions. For instance, are protocol buffers suitable representation for your data structures? Also, you should consider if your wider project, for instance, your web clients, do they need to have wide browser support? Because HTTP2 is still not widely supported by many browsers. Finally, there is also the fact that gRPC is a third-party library. So are you okay with adding third-party libraries to your code? And last but not least is the fact that the whole dance with all of the plugins to generate the additional files can become quite cumbersome and complicated. And it can affect your build times, your project generations, and the general client infrastructure work that you might have. However, I really hope that this talk will help you to make those decisions by understanding the capabilities of gRPC, but also their not so good sides. And if you're already using gRPC in your projects, then I hope that you learned a little bit more and that you've expanded on that knowledge. With that, I will say thank you. You can scan this QR to get access to the demo project that I talked about. Like I said, the full server and client implementation is there. And on my GitHub, I've also uploaded the PDF version of the files of the presentation. So thank you, and I think we are ready to move to the questions section.
Yes.